Yes, again, good morning. My name is Marcello Cirillo, and I'm going to present our work on human-aware robot task planning. So the motivation behind our work is quite simple. Robots are entering household environments, and new possible applications raise new challenges. We do not only want the robot to take into account the human when it's acting, guaranteeing its safety and comfort, but also planning time. So in this case, for instance, we have a vacuum cleaning robot deployed in an apartment, and this will be the running example of my presentation. And we would like the robot to understand that the human is cooking, and then infer that the human after will probably eat. And therefore, the robot could postpone the cleaning activity of the kitchen when the subsequent dining activity is over. I start by defining our human-aware planning problem. Then I will do a little bit of technical details. I will show a full system test case, and finally, I will spend a few words on the performance evaluation. So we define a human-aware planning as applied to situations in which there is a controllable agent, that is the robot for which we want to plan, and an uncontrollable agent, that is the human in this case, whose action we can only predict. So we do not want to plan for the human. If we have this simple example, we have a sequence of predicted actions of the human. We do not predicate on those. We give them as granted. And I will not tell now how we get those, but we have them. So when we want to plan for the robot, for the cleaning robot, for instance, then the policy of the robot must take into account this sequence of actions. For instance, the cleaning of the bedroom should occur after the human has used it, and for sure not during the human is using it. So which are the functionalities that we find useful to plan in the presence of humans? First of all, we would like to support multiple hypotheses of the human plan, because we are only predicting the actions of the human. So multiple hypotheses are more than reasonable. We would like to support temporal durations of actions, because we would like to have a synchronization between the actions of the human and the ones of the robot. The possibility to specify interaction rules between robot and human, and support partial goal achievement, because a household robot is better if it does its best rather than nothing. And then we would like to use observations, but not from the robot side, but the system should be able to observe the outcome of the activities of the human, and then use them in the policy of the planner. But we will see a little bit of this soon. So the definition of the action is quite classic. We have preconditions, duration, cost, transition, function. The only difference is that we have a set of actions for the robot and one for the human. But in the case of the human, we do not want to use preconditions at planning time at the specific step, because we do not want to predicate on human actions. And it must be clear that human actions can both introduce constraints for the robot, like we do not want the robot to clean a room in which the human is sleeping, for instance, but at the same time can introduce also goals. So if the human is cooking, then the kitchen can be marked as dirty also if it was not before. So from actions, we pass to agendas. An agenda is a finite list of consecutive human actions. And therefore, it's an input for the planner. This part, the agendas, we do not want to plan. It's just something that the planner takes and uses to do the robot policy. In classical planning, we have states that define the state of the world. We need something more for human-aware planning. So we have to swap from the states to a situation. And we define the situations as a state. Then we have 3 extra slots, so to speak, in the tuple. We have the robot time, the human time, and those indicate the time at which the last action of the robot and the human has ended. And then we have a human agenda, that is the sequence of actions that the human will perform. So let's take this example. We start from these situations in which the state is S. Then we have the time of the robot at 5. That means that the last action of the robot ended at time 5. And then we have a human time 3. That means that the last action of the human ended at time 3. And an agenda composed by 2 actions that have both duration 4. So when the planner tries to apply an action of the robot, the cleaning action in this case, then in classical planning, we would just check the preconditions in state S and then apply the action. But here is a little bit different because the cleaning action will end after the watch TV action of the human. So what we do is, first of all, we check, of course, the preconditions in state S and the interaction constraints. Then we apply the action of the human, obtaining a new situation in which the human time has been progressed and the state has been changed and modified by the outcome of the results of the human action. We check again preconditions and interaction constraints, and then the planner can finally apply the action of the robot if everything went smooth before. And so in this case, we obtain a final situation that is a new state that considers also the effects of the robot action. The time of the robot has been updated, and as you can see, the human agenda, when we apply the first action, is reduced because one action has been consumed. And this works very well if we have full observability. But when we have partial observability, we have to step from belief states to belief situations. So a belief situation is a probability distribution over situations. This way, the robot can have alternative hypotheses both on the current state of the world, but also on the human plans. We use observations as a result of actions of both the robot side, in this case, a sensing action, and on the effects of actions of the human. So, of course, different observations will lead to different belief situations. We define a human-aware planning problem by 5 items. First of all, of course, an initial belief situation in which we can have also alternative human agendas. Then we have a set of goals with associated values because we would like to weight what we think the robot is what is most important that the robot should do. For instance, in this case, we assign much more value, or slightly more value, well, it's not that much, to the fact that the kitchen should be cleaned, so the dirt of the kitchen should be equal to 0 at the end of the plan, rather than to clean the bedroom. Then we use interaction constraints that says what it's okay or not okay for the robot to do, but also can be more proactive, like a sequence of actions of the human would lead to a constraint of the robot to act and not only not to act. In this case, continuing on the example of the vacuum cleaner, we have that the robot should not clean a room in which the human is performing its main action. Then, of course, we have a set of robot actions defined with name, precondition, results, cost, and time. And finally, we have also the human action, a set of human actions that are equal to the ones of the robot, but without preconditions. What we obtain is a policy. A policy, of course, is a graph. And each node is assigned a belief situation. Then to each node is marked with the action of the robot. So in this case, the robot stays in the robot docking. Here, it moves to the kitchen and so on. And the edges are marked with observation sequences. It shall be noted that observation sequences can be both on the robot side and on the human side. Observation on effects of the human actions and observations, sensing actions of the robot. So in this case, if we have 2 agendas, and we can discriminate which will be we can split the belief situation, and each belief situation resulting will have only one situation inside, because if we observe that the human has prepared a meal, then we know that the next action would be to eat dinner, and the other way around, if we watch TV before, then it will after go out. So we solve a planning problem with a degree P if the value of the policy is at least equal to P. That is, we calculate the value of the goals at the end nodes, and then we backpropagate, and we obtain a full value for the full policy. And to be valid, no interaction constraints should be violated in any belief situation. These are hard constraints that are valid for all nodes. We implemented these new techniques using an extending PTL plan. PTL plan is a progressive conditional probabilistic planner that is on its turn an extension of TL plan. The extensions that we did are basically in 3 points. Okay, this is a very high level algorithm, but doesn't matter. I mean, what it matters is that now we check continuously interaction constraints. We progress the human agendas as human actions are consumed. And finally, we compute the values of those of the nodes using the values of the goals. Once we implemented that, we wanted to test it in a real environment. We wanted to have a full system test case. So we had a proof of concept experiment to demonstrate the possibility to integrate human-aware PTL plan, the name of our planner, into a wider framework. Then we wanted to check the capability of this planner to work online. And we wanted, in general, to check the feasibility of our approach to human-robot interaction. And this is the wider framework in which we place our planner. The core of my research, of course, is the planning technique itself. So the other modules are not inferior, but it's not my main focus. We have a human plan recognition module that takes in data from sensors and then generates the human plan forecast, that is the human agendas. Then we have a monitoring module that each time that this forecast changes, then triggers a planning signal. This is a continuous process. So every time that we have a new update, that the agendas change, the replanning is triggered. And then once the policy has been created, the actions of the robot are executed, and the results of these actions are fed back to the planner. So in case of replanning, we can adapt our initial belief situation. The test of the system was performed in a real environment. This is a small reproduction of an apartment with a bedroom, a small kitchen, and a living room. A user, that in this case was me, spending many, many hours in this teeny tiny room, executes morning activities in this case. We have performed many more experiments, but this one was a very explicative one. The data is always collected from real sensors. The system can recognize 8 possible human agendas, so fixed agendas that we predefined. The plan recognition was performed online, and the robot policy was also executed in real time. So this is an example. We are at time t0. At time t0, 6 out of the 8 agendas have been ruled out of the possibility. So our plan recognition module tells us that these are the only 2 possible agendas. Why? Because they start in the same way. So we have breakfast at the beginning, and then the human starts to relax. And we are still not far enough in the execution. The human is not far enough in the execution to understand which one of the 2 is the right one. But the planner, when receives these 2 policies at time t0, knows that there is an observation here that can be made. So if the relax activity is over, then an observation will be available to branch the possible policy. And this is what happens. So the planner starts to plan, and then using these observations, 2 branches are created. So we have an upper branch that should be executed in case no observation is observed, and a purple one that should be executed in case the branch actually, the activity is this one, the agenda executed is this one. I was executing this one because I preferred to be sitting and I didn't feel like going to bed. But anyhow, the plan was executed correctly, and the planner branched correctly, executing the upper branch. Please note that the upper branch, if executed with the other agenda, would result in a conflict, because the robot would clean the bedroom when the user is actually there, and it's also valid the other way around. So we wanted also to have some performance evaluation. It's not a deep one, and we plan to do much more. But for the instance, we wanted to check if some pruning algorithms, suboptimal techniques like control formulas, could be applied also to our extended framework. Because we need a policy in a less than 1 minute, because we would like to have, our finest granularity is 1 minute, and we would like to have the policy before this this minute is over. So we know that these formulas work with the PTL plan. We wanted to check if they do a good job as well in our situation. We use formulas of this, with this formalism. In this case, I will not dig into details. In this case, it's simply that if a robot is in a room that should be cleaned, and it can be cleaned, then it should stay there and clean the room and not move around. Actually, in the paper, there are two scenarios, not only the cleaning one. There is another one with a moving table, but I will not mention it here because it would be too long. First, we explore the state space without using control formulas, and then we use the control formulas to verify how much we sped up the search. We tested the planner on 3 dimensions: the number of applicable robot action instances, the number of human agendas, and the number of human actions per agenda. The example that I will show is quite wide because it's been tested on 450 automatically generated problems. So these are the results without control formulas. You should know that this is the place of interest for us because in real time, in the real world, we basically almost never have problems that are bigger than this, because this is the number of human agendas, 5, 7, and 9, and these are the numbers of the actions, human actions per agenda. As you can see, also in this set of problems, this is the 1 minute, this teeny tiny line is the 1 minute line, and most of the problems exceed this time by far, and this is something that is undesirable for us. And the progression is quite steady. Using the control formulas, we have near optimal solutions. A full analysis of these results is in the paper, but we can cut off 1 order of magnitude the search space. So in this case, for instance, in our case of interest, we have that almost all problems, apart from 3 outliers, unfortunately, most of the problems are confined well below the 1 minute limit that we need. So the main contribution of the paper is the formalization of techniques that could be applied, and we hope will be applied to human-aware planning. We implemented the actual planner. We tested our planner in a real scenario and as a standalone component, and I think that's quite strong because we actually placed the planner in a real environment and we worked with it for many, many days. And our future work would be to deal with multiple humans and multiple robots and to have human plans with non-deterministic actions. Actually, I also have another small dream that would be to have actions of the human with non-deterministic time duration. But this could lead to an explosion in complexity. If anybody of you has an idea of how to solve that and can give me a hint, it's most welcome. Thank you.
If I understood correctly, you don't consider that the human would respond to what the robot does?
Well, in this example, no. In this example, no. We have another example in which this is not totally the case because the robot becomes a butler in the second example, like bringing drinks. So the human will be utterly pissed off if he doesn't receive his drink between time.
So my question then would be that what I'm missing here is a bit kind of the multi-agent aspect that, if the human always does what he's going to do anyway, then you can basically treat him as part of the environment. Because it's uncertain, but it's fixed.
Yes, this is a little bit controversial because from one side I could agree with you, but on the other side we have dynamic predictions with possible effects, so we do not want to have a fixed schedule. You say treat him as part of the environment. Well,
Unpredictable, but
unpredictable, yes, but partially observable. So it's, we have overlapping with this kind of research, but I don't think treating it only as a part of the environment would be a good approach, especially if we want to go 1 step further in the cooperation.
So I was looking at your results, and it seems like, and I'm looking at the future work as well, and you don't really mention learning these control rules that you seem to use a lot to speed up the results, right?
Yeah.
So I'm not sure what you're trying to test with these control rules. Is it how efficiently you can encode the control rules? Because it's the same problem with DL-Plan, right?
No, I understand what your point. No, in this case it was simply because to test if the same kind of speed up search, the control formulas would work also in our extended formalism as well as they worked before. Now, so far we didn't think about learning. That could be quite a cool idea. I don't know if I'll have the time to go in that direction, honestly. But yes, in this case, it was only to show that the extended formalism still could stand and could use the same kind of control rules.
Your approach allows you to plan robot activities taking into account the human agenda and constraints for the robots. But as far as I understand your work, you do not plan with coordinated actions between the human and the robot. And the second question, can you extend this to human-robot communication, where the agenda is not given initially, but can result from an explicit communication?
So I'll answer first the second because it's the one that I like most, because it's one of the ideas that I really have, and I would love to introduce that. So far, we tried the system in general, but yes, it's my point that if the human could communicate effectively, and like saying, well, I'll go out from now to noon, then the robot could plan accordingly, and we should not rely on a plan recognition module. And this could be even more applicable, because in this case, we could have much more, This is just to the study of the formalism and some examples. But yeah, absolutely is a direction in which I would like to go. The first one was, again, sorry? Coordinated action. Well, not completely, because in the second example that we have in the paper, the robot becomes a butler bringing drinks to the couch for the human. So there is kind of a coordination, but the coordination is not in the sense that we ask the human to do something. It's just that the robot provides some kind of service according to some specific rules. So far, we thought best not to involve the human in the control loop to ask for. I mean, I know that there are works, quite good, excellent ones actually. If I remember correctly, Rashid Alami is working on that. And I've seen his papers and I really like his approach, but our is kind of complementary. We do not want to plan for him as well.
To consider agendas as sequences of actions.
Yeah.
Don't you think that maybe also one could consider agendas as kind of a routine, like a finite state machine that routinely goes through the same action over and over, and so that you can keep it there and the robot can react to this routine?
The reaction, I mean, I'm not sure I understood exactly. Do you suggest a reactive behavior of the...
Instead of considering a single action,
Yeah.
considering essentially as an infinite set of runs of some kind of finite state machine.
No, we didn't think about it. Honestly, I didn't think about that. I could be... No, I should have give some thought, and if after we can discuss a little bit, could be quite interesting. Thank you. But, yeah.
It seems like in this example, you could greatly use some sort of smoothing. It doesn't seem like the semantics of what the human is doing in the room at a given time should really matter for the cleaning robot. I mean, does it matter if you're sitting in the kitchen watching TV or eating dinner? I mean, either way, you're in the room. As far as the robot's concerned, you can't clean in that room.
Yes, but this is a special case. This is one example that was my running example. We have other examples in which this matters. And besides, there is another problem. I mean, this is a coordination of modules as well. So we do not observe the human being in a specific room sometimes, but through other sensors, we infer that he's sleeping. So the observation then becomes the fact that he's finished his sleeping process, or, well, finished sleeping because it's a human, it's not. But yeah, so there are two reasons why we do not do that. First of all, because this is just one of the examples that we have and one of the test domains. In others, this matters. And second of all, to give a meaning to the observations that we have.
Okay, well, thanks again for the
Thank you.